Where we finished off in the last talk was this question of, well, how does stuff flow through to the larger scope of the program? And surprise, surprise, the next talk, I didn't know that was going to happen, so really it's down to Alex and Tobias who planned all this. Hemant here is actually going to talk about this, the idea of substructural information flow, and it's captured nicely in his title slide in that we have these words, and each of these words are in different colors. And what that symbolizes is that different information can flow through different parts of the program. Yes, I did once study semiotics, but only after I got my PhD. Thank you. Last talk, you have something like 25 minutes without hesitation. Remember to deviation.
Okay. Yeah, so I want to talk to you about some of the thoughts and preliminary work Jonathan and I have been doing on sort of rethinking the foundations of information flow and sort of seeing where we can go with it. So I want to start by first explaining sort of what information flow is for anyone in the audience who doesn't know. After that, I'll explain our reformulated sort of foundations of information flow, like based on parametric polymorphism rather than lattices, which we hope proves to be more familiar than the how people have done it so far. And finally, I'll talk about how this polymorphism-based foundation of information flow leads naturally into an analysis of information flow, from a substructural lens, and I'll make clear what that means exactly. But first, I'll provide you with my very, very opinionated guide to information flow. And for anyone in the audience who already knows about information flow, I hope I can win you over by the end of this, but it's probably not very similar to anything you've seen before. So throughout the talk, I'll have this sort of color coding going on. It's not essential to understanding, but basically, so here, like pink means source, purple means source destination, blue means destination. You'll know what that means when I get to it, but the hope is that at a glance you'll be able to parse the slides. So I like to start off talking about information flow by presenting these blocks, these circles. And the idea with these circles is going to be basically, you can always start in the smaller circle and go to the larger circle, right? But you never go from the larger circle to the smaller circle, right? And okay, so the canonical example of like what people use information flow for is protecting secrets, right? So you can start with public information can flow into secret information, right? That's okay. That doesn't leak any secrets. But it's not okay for secret information to flow into public information, right? Because that does leak secrets because more people are able to see public information than secret information, right? And going to something weirder, right? If we look at ML modules, right? At the type level, it's okay for type information about the client to flow into the module, right? But it's not okay for like module internal types to flow into clients, right? Like it would be very bad if like an ML module's abstract type was revealed to its clients. And graduating to something even weirder, right? So I don't want to claim that this is like what you would actually want to do to manage concurrency in your programs, but just to give you an idea of what information flow specifications look like, if I have some code executing in a sequential context with four-point parallelism, right? That information from the sequential context can flow to task 1, and information from task 1 can flow to task 2. But it would be very bad if potentially if information could flow back into smaller circles. Why is that? Right? Because we don't like deadlocks, right? So like if information can flow from task 1 to task 2, and then back from task 2 to task 1, we have a potential for a cycle, right? And one very onerous restriction for preventing deadlocks is basically to say, okay, all information must flow monotonically, right, according to this sort of circle intuition. Right. Okay, so you can imagine that, okay, so in this case we have like password being the larger circle and standard out being the smaller circle, right? So you can imagine it says, standard out can put a password, but a password can't put a standard out, right? So we're trying to protect some password data, right, from leaking. And we have some miscellaneous program data to do with this like password checker program that we're presumably implementing under this information flow policy. So the way to begin understanding information flow is to say, okay, if we concatenate two pieces of miscellaneous data, that gives me back some miscellaneous data, right? So purple, concatenating purple and purple makes purple, right? But concatenating like miscellaneous data to some password data makes blue stuff, right? The idea is that we want to infect we want to have password data be infectious, right? Because like this concatenation result contains information about this password data. So the idea is that standard out can float a password, right? But password can't float a standard out, right? And you can understand all these in terms of lattice operations, right? And if you don't know what a lattice is, I hope I am able to prevent you from being scared off. It's not anything complicated. Basically, it's exactly what I just explained, but like in terms of like it's happening at the type level, right? So when you concatenate two things at the term level, at the type level, what's happening is you're joining two purples to make purple, right? Here you're saying, okay, I'm joining purple, which is lower than blue, with some blue thing to make a blue thing, right? So I'm using this least upper bound operation to find the higher of the two things that I'm joining together, right? And this gives me this property that I want password data to be infectious, right? Okay. And likewise, if I have standard out being partially ordered less than password, right? That means standard out can put a password, right? But if I don't have that, then the thing on the left-hand side cannot float to the thing on the right-hand side. That makes sense. And I want to do a quick demonstration. So I've got FlowCamel fired up here with my kind of terrible homebrewed IDE tooling. Can everyone see this? Okay. Oh, you can't see this? Okay. Bigger? Bigger. Okay. Yeah, let's make it bigger. I can't switch black on. Oh. Is it better? Okay, awesome. Okay, so let's fire up FlowCamel here, and let's do, whoops, not that. Right, okay. So the idea here is, okay, so on this first line, I'm declaring so I'll actually reveal this line by line. So on this first line, I'm going to declare some password data that's indicated by being predicted by this password label, right? And I've set it to the name of my cat, and I'm gonna initialize a session token that has this token label, right? And I'm declaring this check function where all it does is it closes over password and checks if it's string input is equivalent to the password. And you're already seeing here that it's FlowCamel is starting to infer some lattice constraints, right? On the check function. Specifically, it's saying password data has to be able to flow to the standard output, right? Or not to the standard output, to the return value of the function. And then I declare this authorize function, and it starts to blow up on me, right? And I don't want you to parse this type. I just want you to recognize that this is not an easy type to read, despite despite the implementation of this auth function actually being quite simple, right? Because all it's doing is it's checking if this password attempt is correct, and if it is correct, it's passing this session token to this callback that's being passed to it. So that's a hardware function. Otherwise, it just returns false for the entire function, which is not a particularly complicated signature. And the other point I want to make here is, okay, let's fire up not FlowCamel but OCaml now, right? Okay, I'm getting an error, but that's fine. Let's fire up OCaml, and let's see what OCaml says about these types. So let's utop use authorize. Right, and I want you to notice basically like all the complexity here is coming from the information flow side, right? These are not computationally complicated functions. And the other thing I want you to realize is, okay, so if I declare this new function here first, right, which just takes two arguments and returns its first argument, right? OCaml infers a perfectly sensible information flow type for it, right? I want you to notice that, okay, this specification that says first takes in a take A and a take B and returns take A, that completely describes the information flow content of first, right? On the other hand, if I want to describe the information flow content of this both function, which takes in two arguments and just adds them together, this int type is not sufficient to describe the information flow stuff that's happening there, right? So that's the demo. And okay, so the idea here is going to be we're going to leverage this ability of OCaml to use polymorphism to talk about information flow, and basically try and take that to its logical extreme, right? Okay, so this is the basic syntax of our system. E is an expression, AB are dependencies, int is a type, And you can read this as E of type AB int it's an expression E is dependent on data from sources A and B with type int. So A and B describes how something was computed. It's a behavioral property, right? We've heard a lot of that here. And int describes like the layout of the thing in memory. It describes what it is. And the idea here is that we're going to track information dependencies and types where flows induce dependencies. So we can write down the first function we saw earlier as just same implementation, but now it's A int to B int to A int, right? So x is of type A int, y is of type B int, and the return value is of type A int because we just return x. And now we can actually assign a reasonable information flow type to both functions, right? We're just leveraging the existing mental machinery for parametric polymorphism to say, okay, well, now the return value is dependent on both A and B, right? And we can declare this branch function as well, which expresses a more complicated case of information flow, where basically it takes in a Boolean and it takes in an integer. It branches on the Boolean, and if the Boolean is true, it returns the integer. Otherwise, it returns 0. Because we branched on the Boolean, the return value of the function betrays something about the value of this Boolean. So we have to track the indirect dependency there, and therefore propagate this A, the return value of the whole function. And because we return an x in one of the branches, we propagate this B, right? Oh, whoops. And okay, so I want to sort of justify to you why I think this is like hugely, massively simpler, right? So I've sort of taken the authorized function from FlowCamel and simplified it to this sort of symbolic representation. I've given myself certain affordances, so don't read too closely into this, but like approximately, right? This is saying the authorization token has to be able to flow into the callback, right? Because we're passing the token to the callback, password and the password data and the password attempt and the return value of the callback all have to be able to flow into the output of this authorized function, right? That's what that's saying, and that's like a reasonable lattice-based information flow type for the authorized function. So how do we simplify this? Okay, so we have this lattice constraint that says token has to be a sublabel of B, right? But instead of leaving it as that, we can just say, well, let's first make this like sort of line graph representation of the lattice constraint. Let's bracket it up to use our syntax, right? And let's just execute this, right? Let's just say, oh, we know token has to be able to flow into B, so why don't we just replace B with token, right? Because we're just running the flow statically. And to use a more complicated example, right? You can turn this other lattice constraint also into this sort of tree-like representation, and then we're gonna bracket it up to use our syntax, right? So it's gonna turn into for now we're gonna be able to execute the join of all of these labels into that. So password join A join C just turns into that. On this side, if you're not using our syntax or if you're not using our semantics, you can't simplify this at all. This is irreducible, right? So we're already better, and then we just execute the flow, right? We just execute it, right? And then we're done. So this kind of not so great type turns into this really quite declarative specification of the information flow content of the authorized function, right? So it's saying I've taken an A string, I've taken a callback which as its argument takes in a token int and returns a C bool, and my whole return value is dependent on password and A and C, which is approximately what you would expect. You might ask, why is a token in here? Well, that's accounted for by the type checking of this function. So C is polymorphic. So token, you might imagine that the token dependency is like hidden inside C, kind of, right, in this type. And this gets like arbitrarily complicated, right? So one thing we're actually exploring is whether like lattice-based information flow is doomed to like exponential explosion cases. So I have lattice constraints that are like megabytes large. So I'm being very fair here. And this is an example of a sort of like type that regularly comes up when you're doing functional programming with FlowCamel. And this whole thing reduces via our computation to this thing, right? And you might wonder, like, okay, what's the catch? Like, why are you able to do this? It turns out, for those in the audience who like to play in the land of logic, it's a beautiful idea, and I found it out recently. This wasn't an explicit design goal. The difference between this and this is exactly the difference between the constructive script key semantics for modal logics. This is known as the relational approach, and this is known as the algebraic approach. So if that means nothing to you, that's fine. But there's like a very, very sound theoretical justification for why we can do this. It's because we're sort of doing information flow in a very constructive flavor. Okay, so now let's do substructural information flow. So some questions you might ask upon seeing our syntax. Is xy the same as yx? Is it? Is xy the same as xyz? Is xx the same as x? Contraction. Okay, so what does it mean to get rid of these rules, right? So these are pretty familiar. They're just the normal substructural rules, but what do they mean for information flow, right? So with weakening, we can take the identity function as, you know, if x has dependency bluefish, then if the body is just x again, then we can weaken a yellowfish onto the body, onto the return type of the body, and just have x be typed as bluefish, yellowfish, right? We can do that. In the absence of weakening, we can't lie about the dependencies we're witnessing, right? So we have to say that the body is the type bluefish. It would be a type error for us to include yellowfish, right? And interestingly, the branching function I showed you is a type error in the absence of weakening, because you normally have to weaken the yellowfish here, or sorry, you normally have to weaken a bluefish here, right? Or sorry, you normally have to weaken a yellowfish here, right? Because otherwise, because this branch witnesses a yellowfish, 0 has no dependencies, right? So it's not actually witnessing a yellowfish. You have to use weakening to reconcile the types between the two branches. And in the absence of weakening, there's no way to do that. So there's no typing for that term. Okay, contraction, approximately what you would expect. So with contraction, you can type this doubling function as just like bluefish of bluefish. But without contraction, of course, because you're using x twice, you have to type it as 2 bluefish in the return value. And exchange is similar. If you take in a bluefish and yellowfish, and you use the yellowfish first and then the bluefish, in the presence of exchange, you can just lie about it and say you used it in any arbitrary order, in any permutation you please. In the absence of exchange, you can't do that. You have to be honest about the order you used it in. Okay, so those are all play examples to build intuition. But what is this actually useful for? So this is cool because so in the absence of weakening, it turns out that we get capability reasoning, right? So if you look at this like ML module, right, it has this existentially quantified label. It has this module internal label. This is like an abstract label. Diamond, right? And we have this authorized function that takes in a password and either gives you back a diamond, a unit with a diamond dependency, or a unit without a diamond dependency, right? And the idea is that if you have a bunch of sensitive operations in your program, you don't need to instrument authorization logic everywhere, or you don't need to wrap up your types in a bunch of phantom types if you're familiar with that pattern, basically expressing the fact that something happened, some kind of valid authorization happened. You can just add on the tag to any of your types. This diamond tag that witnesses the fact that yes, you at some point in your computation you had the correct password. And for a more fun example, we have this bank thing. So we have this abstract type money bag. We have this label coin. And okay, so there's a method that gives you an empty money bag. There's a get coin method that kicks in a money bag with some arbitrary dependencies A. So this get coin function is polymorphic, and gives you back another coin in the dependencies of your money bag, right? And we have this transact function that takes in a password and takes in a spending function, right? Where the return value of the spending function is the dependencies in the return value are constrained to be at most 3 coins, right? So this is like your parents saying, oh, you can only spend 3 coins a day, right? So you're asking your parents so if you can buy something, and they're like, oh, what's is that below your daily spending limit, right? And the way you use this is you say you call transact on password and the name of my cat, and you call get coin twice maybe, right? You don't have to call it 3 times. You only have to call it twice. You can only call it twice on empty, and then it just executes the spend side effectively for you. So this is kind of like a resource limiting API. You can read it that way. Yeah. Oh, 5 minutes. Yeah. Substructural non-interference. I'll be honest with you. I have to butcher the definition of non-interference in a really horrific way to make it bite-sized. The full one is beautiful, and you should talk to me afterwards. about like all the interesting things you can do with it. But if you want like just like the tip of the iceberg, the definition of non-interference is that you mustn't be able to turn something you cannot observe into something you can observe. Okay, that's like the idea. So in the case of passwords and standard out, right? If you don't currently have like access to the password, you should not be able to gain access to the password, right? If you imagine that you're some you're some unprivileged observer on the program. And the central idea of this work is that the structural rules define your powers of observation, right? They moderate them. So it turns out that both of the examples I showed you are actually like fully sound by substructural interference, and they're sound in a very, very strong sense. They're sound in the sense that substructural interference immediately gives you capability safety when you've dropped weakening, because what it says is that, well, it would be a violation of non-interference minus weakening to be able to get a diamond dependency without actually executing this operation, right? So in the original version of our system, we actually didn't have weakening because we didn't realize this whole connection. We only had it be the case that you could get a dependency if you did some computation that witnessed that dependency, that made that dependency for you, right? So substructural non-interference in that case is saying exactly this. Like, you cannot just give yourself a dependency if you don't have it, right? We don't have any sub-labeling. And similarly, we have like sound resource bounding, again by substructural non-interference. In the presence of contraction, having 1 coin is the same as having 19 coins, and having like 17 coins is the same as having 4 coins, right? It's the same thing. In the absence of contraction, I can't do that. It's banned. It's no good, right? Okay, so other cool. Yes, exactly. So I don't want to claim that this is entirely like standing on its own or anything. Granulism is some really, really awesome work by Dominic Orchard and friends. It acts as a framework for expressing graded type systems and graded effects and co-effects. Our type system actually embeds into theirs. The real contribution I think here is that substructural interference works on the embedding. So regardless of where you implement this, like if you implement this as like a standalone thing, or as like a compiler extension like that, or as like a language extension in some other context, right? Substructural interference is guaranteeing that if you're doing this kind of reasoning, you have very, very deep and powerful sentence properties about it. And of course, there's lots of other like really awesome work on reasoning about behavioral types. The difference between information flow and these things is that information flow is a matter of talking about the past of a computation. So if I'm holding some computation, information flow tells me what that computation did in the past, whereas session types and choreographies, which are a modification of session types and type state, what those tell you is if I'm holding a computation, what can I do with it in the, like what is the structure that I can cause it to take in the future, right? So it's sort of this interesting interplay between past and future that distinguishes the two. And that's the end of my talk.
So on one of your earlier slides, you showed the type for plus, where you add 2 integers and return an integer, and you annotated this with 2 type variables, a and b. And the question is this equivalent to the type where I only use 1 polymorphic variable? Because I ask this question because in the thesis of Stephen Dolan on algebraic subtyping, he shows that from a subtyping point of view, it's equivalent if you only use 1 type variable. Yeah, and here both type variables co-occur in the output position, so they're equivalent. Okay.
Do you want to ask the question? Lionel, do you want to ask the question, or do you want me to ask it for you? Well, the question is, you know, you were busily dissing Leonard's talk, saying, "Oh, we don't have things like phantom types and stuff, but we've just got effects." Right, and the point of the previous talk was, we don't need extra effects. We just have phantom types and subtyping. I will now put you both into an octagonal cage, and.
Hi, thanks for the talk. Yeah, I agree with David that this looks a lot. If you do have weakening and contraction, this looks a lot like algebraic subtyping, right? It seems to be equivalent. So you may get inspiration from there to simplify these types, right? So that you can only have. But I wonder. So what's the type of a function that takes some string and puts this string temporarily in some list of passwords? Okay, so it puts it in a list of passwords, and then it forgets about the list of passwords, and it just returns the string. Extracting it back out of the list of passwords, then it's going to No, you're not extracting back. You're passing what you received as a parameter. So does the fact that you put it in a list of passwords kind of influence the type of the parameter?
Unless it's done immutably, it shouldn't.
It does.
Merely the fact that you put it in a list of passwords, as long as the whole game is to talk about observational equivalence, and as long as the fact that you did that is not observable, then it shouldn't influence anything.
Then I guess it's basically like Stephen Dolan's algebraic subtyping. It's not based on unification, and you don't get these weird flows that don't make sense, right? Yeah. Cool. Yeah, that's it.
Okay, so I have a question. Maybe it would be good if you went to the slide where you had the example with the purse and the coins about the contraction or lack of contraction. So there, yeah, if I see it. Oh, okay. So here you are sort of conflating something like you are using this annotation that you have to reason about effects, basically, in the result of this function passed to transact, right? And
Formally it's an effect indexed by a long way.
right, but in other slides that you have, you are basically saying that you can also use this annotation to track something like provenance, right, of values, like saying that, you know, like this is a secret and this is public information, right? So it seems that you are sort of like, does it mean that like you must like conflate these two meanings of this annotation, or do you have a way around it so that you don't need to conflate what these annotations mean?
Yeah, so I wouldn't phrase it as conflating necessarily.
Okay, I'm just trying to puzzle it out because it seems to me, I mean, the conflating question came from the fact that, you know, you will be using some of these things to reason about provenance, some of these annotations to reason about like what effects happened, and then like the different labels will start to flow into annotations where they aren't meant to be, right? And I would expect that this can like this can actually manifest in some problems, like in what you can and cannot type.
Yeah, I'd be curious to see. Yeah. So. It's impossible for like the presence of one label to like remove a different label or something like that. It's all.
Mm-hmm. Okay, I'll think about this, but maybe we should take it offline.
Other questions or discussions? Because we should clap and go to lunch.